All right, hopefully you guys have had a chance to look at your worksheet. You'll notice it's 3 pages long. The first page is just practice on regular dimensional analysis problems. We did this day before yesterday, but I just kind of wanted to get you back into the groove of thinking about those kind of problems. Hopefully you turned in your activity worksheet A3 for a grade. And at the end of the class, you'll turn this 3 page worksheet as well. And now I'm going to teach you how to do not just the first page, but also the second and third pages with a new concept. So let's first go over an old concept of dimensional analysis, which we started off. So let's consider this problem here on the board. Convert 17.5 quarts to liters. And within parentheses, they've given us what the conversion factor is. 1.06 quarts is 1 liter. So we need to convert that. Over here, we're using non-standard units. Quarts are not the metric system, but the point of this problem is just to get you practicing how to set up a problem like this. So when you set up dimensional analysis, start off by putting your division symbols and your multiplication symbols, as many as you need. For now, I'm just putting 2 division symbols. If I need more, I'll add more later. And the first step should always be on the top left-hand corner, write what is given. In this case, 17.5 quarts are given to us. So I wrote that on the top left-hand corner. Step 2, mindlessly copy paste just the units on the bottom right-hand corner. So I'm not worrying about numbers right now. I saw that there's quarts at the top, so I'm going to copy paste quarts at the bottom. Now you're going to use your conversion factor. 1.06 quarts is 1 liter. So since I mindlessly copy pasted quarts, now I kind of know what number needs to go there because there's only one number associated with quarts, 1.06. So I put 1.06 at the bottom. But since it's associated with 1 liter as a conversion factor, I must write 1 liter at the top. Now for this problem, I'm going to stop here with dimensional analysis because when I read the question, it says 17.5 quarts to liters. And liters is my destination. Like that is my expected or desired unit. And if you'll see in the top corner, I have liters, so I can stop there. I'm going to cancel out quarts because there's one at the top, one at the bottom, and when you divide something by itself, it cancels itself out. So that leaves me only with liters as my unit. And if I multiply 17.5 times 1 divided by 1.06, turns out 17.5 quarts is the same as 16.5 liters. Let's do another problem. Let's try to convert 3,598 grams into pounds. For this, unlike the previous problem, I need 2 conversion factors. Not 1, but I need 2 conversion factors. So one of my conversion factors is to tell me how to get to pounds. 2.20 pounds is 1 kilogram. But what even is a kilogram? I mean, when I look at my question, there is no kilogram. It says grams. So I got to know how to convert that too. So if you look, the second conversion factor is 1,000 grams is 1 kilogram. So basically what I'm doing is I'm teaching myself to convert grams to kilograms and then kilograms to pounds. Now, I don't know how many of these I'm going to need, so I'm just going to draw a whole bunch of them. In this case, I drew 5 different blanks and put multiplication signs between them. If I need more, I'll add more. If I need to take away some, then I'll erase some out. But let's start the problem for now. Step 1 of any dimensional analysis problem is always the same. Copy the question in the top left-hand corner. So 3,598 grams goes in the top left-hand corner. Step 2, mindlessly copy paste your unit, grams. Now that you've done the mindless work, we have to figure out what number goes with the grams. So now we look up to our conversion factors. The first conversion factor is kg in pounds. That doesn't apply here because we're looking for grams. But that second conversion factor is 1,000 grams to 1 kilogram. So I got my number for grams. If I put grams at the bottom, then I must put 1,000 next to it. But if I put 1,000 at the bottom, like that 1,000 grams, then 1 kilogram must go on top because that's what my conversion factor says. 1,000 grams is 1 kilogram. Now that I've done this, I'm looking at my question. The question says convert grams to pounds, not grams to kilograms. So I'm not done yet. I'm going to mindlessly copy paste my unit kilograms down to the bottom. And now I'm going to look back at my conversion factors and, ooh, I have a new conversion factor. 1 kilogram is 2.20 pounds. So I put 1 next to the kilograms that I just mindlessly copied, and on top I have to put 2.20 pounds. Now the good news here is that when I read the question again, convert grams into pounds, pounds is my final destination, and I've reached my final destination, 2.20 pounds as my unit. So I can take away those extra blanks, and now I can start canceling out my units. So notice how grams and grams cancel out, because one is at the top, one is at the bottom. Kg and kg cancel out. And so if I multiply every number at the top, 3,598 times 1 times 2.2, the whole thing divided by 1,000, I get 7.916 pounds. Now the next problem we're going to do as practice is actually the problem in your worksheet. It's problem number 1. So take a look at the first page of your worksheet, top problem number 1. 5,400 inches to miles. So you need 2 conversion factors here. And if you look at the entire list of conversion factors given to you, the 2 conversion factors of interest are 1 mile is 5,280 feet and 1 foot is 12 inches. Now the reason that these 2 conversion factors are of interest is because you're trying to get miles down to inches, and you're doing that in 2 steps: miles to feet, feet to inches. Or I'm sorry, the other way around. You're trying to get inches to feet, feet to miles. So again, I don't know how many of these conversion factors I'm going to need, so I'm going to draw like a whole bunch of blanks to prepare myself. And every problem starts the same way. Every problem you have to start off at the top with 5,400 inches. Now that you've started off with 5,400 inches, which is what is given to you, we have to mindlessly copy paste our units to the bottom. Now let me look at our conversion factor and see if I can find inches. Yes, I can find inches. 12 inches makes a foot. So I'm going to fill 12 in by the unit and put the conversion factor on top, 1 foot. Now 1 foot isn't what I'm looking for. Like feet isn't my unit that I want miles. So let's do this one more time. Copy paste your unit in the bottom right hand corner and look at your conversion factors and see if there's a number you can fill next to it. And it turns out that there is a number I can fill next to it, 5,280. So I'm going to fill that number, but I can't leave the top blank. So on the top, I'm going to put 1 mile because that's what my conversion factor tells me to do. Now the good news is miles is what I want. Miles is the desired unit, so let's take away all the other blanks. Let's start canceling out unit to double check and confirm that we have miles. So inches and inches cancel out. I've shown that in red. Feet and feet cancel out. I showed that in blue, which leaves me only with miles as the answer. So multiply everything at the top, 5,400 times 1 times 1. Multiply everything at the bottom, 12 times 5,280, and then divide the 2. The slide says 0.83 miles. That's a typo. Your answer should have been 0.083 miles. I'll repeat the answer. The answer is 0.083 miles, not 0.83 miles. Now I want to teach you 3 new conversion factors that you can use. And you're going to use this constantly in chemistry, so these are kind of important. I want to teach you what the mole is. Once you understand what the mole is, molar mass and Avogadro's number will be fairly simple. So I'm going to focus on the mole first, get you to understand that, and then you'll see molar mass and Avogadro's number kind of work their way in. So in chemistry, when we say 1 mole of anything, it means we've got 6.02 times 10 to the power 23 of that thing. That sounds super vague and super confusing. So let's use some concrete examples here. If I have 1 mole of cupcakes, it means I have 6.02 times 10 to the power 23 cupcakes. That's a lot of cupcakes. That's like having 6 million cupcakes. Actually more than that. Having 1 mole of pens is having 6.02 times 10 to the power 23 pens. That's 6 million pens. And again, that's a lot of pens. So when we say 1 mole of something, or 1 mole of anything is 6.02 times 10 to the power 23 of that thing, it just literally means there's a lot of it. Um, but 6.02 times 10 to the power 23, it's such a weird number. Like, you don't even know how big that number is. So let me try to impress you here a little bit. So to understand how big this number is, let's consider buying 1 mole of iPhones. If you bought 1 mole of iPhones, the number that you see on the screen, I don't even know how to say that number. And because I don't know how to say that number, I've just been saying it's more than 6.02 million iPhones. Um, but I don't know what number exists like that I can use to describe that. If that still doesn't impress you, let's talk in terms of money. If a stranger comes up to you and says, "Hey, you can either have $2 billion cash today, right now, or you can have 1 mole of pennies. Which one do you want?" Most people will be tempted to accept $2 billion because that seems like a lot of money. But the smart people will say, "I want 1 mole of pennies." And I'm going to show you the math behind why, if somebody came to you and said, "Hey, do you want 1 mole of pennies?" without a second thought, you should say yes. The reason you should say yes is if you accepted 1 mole of pennies, work through this slide line by line. Start with the first line. That's how many cents you have accepted. But who cares about cents? Let's convert that to dollars. If you accepted 1 mole of pennies, look at the dollar value you've accepted. That's what, 3, 6, 9, 12, 15, 18, 19 zeros. Like, there's 19 zeros after that 602. That's a lot of money. If you don't know how much money that is, let me just put it this way. If we took 1 mole of pennies and we split them equally among every human being on this planet, which means all 8 billion people, then all 8 billion of us would be billionaires. Like, each one of us would have $752 billion just for ourselves. And that's all because one person offered you 1 mole of pennies and you were kind enough to share that with everybody. Everybody becomes a billionaire. So, the bottom line, what I'm trying to get you to see is that 6.02 times 10 to the power 23 is a ridiculously large number. So, when I say that I have 1 mole of something, it means I have a ridiculously large number of that particular thing. So, if I had 1 mole of cupcakes, right off the bat, you can see having 1 mole of cupcakes is ridiculous because having 6 million cupcakes is probably going to end up weighing more than planet Earth itself. So we can't have that many cupcakes. So we don't use Avogadro's number for big things. We instead use Avogadro's number for tiny, tiny little things like atoms and molecules because it's easier to have millions and millions and millions of atoms or molecules rather than have millions and millions and millions of cupcakes. So let's do an example in chemistry. Take a second to get your periodic table out. If you don't have a periodic table, now would be a good time to hit pause in the video, and there's a set of periodic tables on the front desk of the room. Get yourself a periodic table. You're going to need one. Once you have a periodic table, I want you to look for gold. Gold is atomic number 79 on your periodic table. The reason I want you to look for gold is because I want to teach you what 1 mole of gold is. If I have 1 mole of gold, you already know it by this point. 1 mole of anything means you have 6.02 times 10 to the power 23 of that thing. So if I have 1 mole of gold, I have 6.02 times 10 to the power 23 atoms of gold. Now, if you wonder how much those atoms of gold weigh, so let's say I took all of those atoms of gold and I put it on a weighing scale, they would weigh about 196.97 grams. If you're wondering where I got that number from, that's why I wanted you to have your periodic table, is for you to find gold, atomic number 79, and you'll see your periodic table says that the mass of gold is somewhere around 196.97. So all of those little numbers in your periodic table that's at the bottom of an element is basically telling you if you had 1 mole of that element, it would weigh that much. We call that the molar mass. So the molar mass is quite literally 1 mole of gold. For gold, its molar mass is 1 mole of gold would weigh 196.97 grams. So let's look at molar mass. Molar mass is if you took 1 mole of the element or a compound is more than one element, and you added them all up together, that would be its molar mass. So take a look at your periodic table so you can figure out what the molar mass for different elements are. So let's start with carbon. Carbon should be atomic number 6. And if you look at atomic number 6, it says the mass of carbon is 12.01 grams. What that means is if I have 1 mole of carbon, I would have 6.02 times 10 to the power 23 atoms of carbon, and they would all together weigh 12.01 grams. If I have 1 mole of helium, helium is atomic number 2 on your periodic table, it's the second element, you'll find that 1 mole of helium on a weighing scale would weigh 4 grams, and those 4 grams would contain 6.02 times 10 to the power 23 atoms. Now, if you look at the molar mass of oxygen, oxygen is atomic number 8. And you'll notice that if you had 6.02 times 10 to the power 23 atoms of oxygen, it would weigh 15.99 grams. Now, if you're asking yourself, how can you take the same number of atoms? Like, so far I'm saying, yeah, I have 6.02 times 10 to the power 23 atoms of carbon, same number of helium, and same number of oxygen, and they all seem to weigh different. What that simply means is oxygen atoms are bigger and heavier. So if I have the same number of them as helium, they're going to be heavier just because helium is so darn tiny. Now, how do you find molar mass of compounds? So compounds are different from elements. Elements are anything you can find on your periodic table by themselves. So carbon is an element, oxygen is an element. But if you put them together, for example, carbon dioxide, whose formula is CO2, that is a compound because it's no longer just carbon, it's no longer just oxygen, who are elements. We're just mixing them together in a 1:2 ratio, and it's carbon dioxide. If you mix them in a 1:1 ratio, that's carbon monoxide, and that's super poisonous and toxic. But let's go with carbon dioxide for now, since it's not so toxic. We actually just exhale that, it doesn't really kill us. If I wanted to find the molar mass of carbon dioxide, I would find the mass for carbon, which in my periodic table is 12.01 grams. I would find the mass for oxygen twice because oxygen is O2 according to CO2, so 15.99 plus 15.99. Just add all of them together, you get 43.99 grams. That mass of carbon dioxide is how much you have in 1 mole. So if I have almost 44 grams of carbon dioxide, it means I have 6.02 times 10 to the power 23 molecules of carbon dioxide. So millions and millions and millions and millions of molecules of carbon dioxide will weigh 43.99 grams. Now let's see how you would apply this in a problem. In a problem, like how many atoms are in 234 grams of copper, you would have to use dimensional analysis. And just like the first few problems we did at the beginning of this video, we need to set up our conversion factors. So our conversion factors for this newly learned unit that you just saw are 2 of them. So the first conversion factor is that 63.55 grams of copper is 1 mole of copper. Take a second to figure out, where did I get 63.55 grams of copper? Like, the question didn't say that. Did I just pull that out of thin air? The answer is obviously no. I pulled it out of the periodic table. So according to the periodic table, the mass of copper is 63.55 grams, and I know that whatever that mass is on the periodic table is telling me how much 1 mole of copper weighs. And by now, hopefully, it's been drilled into your brains that 1 mole of anything is 6.02 times 10 to the power 23 of that thing. So 1 mole of copper is 6.02 times 10 to the power 23 atoms of copper. So I have my 2 conversion factors. Now I can draw my little blanks and multiplication signs. And for now, I'm going to draw 3 of them. If I need more, I'll add more. If I need to take away some, I'll take away some. But if you're wondering, like, Miss S, I don't want to keep drawing all these blanks and like adding more or erasing more, how do I know the exact number? List out all of your conversion factors. Like, for example, here in this problem, I know I have 2 conversion factors. Add 1, that's how many blanks you're going to need. So if you have 2 conversion factors, you're going to need 3 blanks. If you have 4 conversion factors, you're going to need 5 blanks, and so on and so forth. So I have three blanks, and now you know that the first step is to write what is given. So notice how I've written what is given: 234 grams of copper. Next step, mindlessly copy just the unit, grams of copper. Now that we've copied just the unit, we're going to try to figure out what number is going to look pretty next to it. And that is where this conversion factor comes into play. 63.55 grams of copper would look pretty damn good next to our unit, so we're going to go ahead and put 63.55 grams of copper. But we also know that 63.55 grams of copper should always be equal to 1 mole of copper, so we've got no choice but to put 1 mole of copper on the top. Now that I have that, let's move on to the final blanks that we need to fill. Copy paste moles of copper, our unit, without even thinking about it. Just mindlessly copy paste that. Now let's look at our other conversion factor to see if we can put a sensible number next to moles of copper, and we can. We can put 1. So 1 mole of copper, according to this conversion factor, is 6.02 times 10 to the power 23 atoms of copper. Now comes the fun part of canceling out your units. So grams of copper and grams of copper cancel out. Moles of copper cancel out, which leaves me with atoms of copper, which is good news because when we look at the question is asking how many atoms of copper are there. So multiply everything at the top. So 234 times 1 times 6.02 times 10 to the power 23. Divide by what's at the bottom, 63.55. The answer that you get is the number of atoms of carbon you have in 234 grams of copper. So here's what I want you to do now. I want this video to be paused to where this screen stays on the board. And while this particular screen stays on the board, I want you to finish pages 2 and 3 of your worksheet. It looks like there's a lot, but it's really only 6 questions that I've tried to spread out and give you plenty of room to work. So all you have to do is fill out those blanks, fill out the conversion factors, and find me the final answer. Good luck with that, and have a great weekend. If you have feedback from me about whether this lesson was useful or not, I would really, really appreciate an email because I'm super curious to know if this worked or not, and I don't want to wait till next week to figure that out. So if you have a minute to send me a quick email and let me know, hey, this was super helpful or this was super confusing, I would really appreciate the feedback. But for now, good luck with that worksheet and have a great weekend.